Okay, now, if we have x, y, z axes and some curve doing something, and not being very specific about that, we can, at any point of the curve, calculate the unit tangent vector. Not writing very well. R prime divided by the magnitude of R prime. We can calculate the acceleration vector. Okay. R prime of t is just your v of t, your velocity vector. Velocity is always in the direction of the tangent, so the unit tangent is the derivative of your velocity vector over the magnitude of your velocity vector, but I write it in terms of r as r prime divided by magnitude of r. The acceleration is the rate of change with respect to time of your velocity vector, which equals second derivative of your position vector. So you're going to have some acceleration vector. Now this curve, we're curving. So let's assume we're speeding up along this curve. But we also need an inward acceleration to change our direction. So let's just say that our acceleration vector is like so, not parallel to our unit tangent vector. We also have the unit normal vector. I'll designate by n. And n equals t prime over the magnitude of t prime. Now there are easier ways to calculate n. We can actually use the acceleration vector and the unit tangent vector to figure out the direction of n. But right now we haven't dealt with the acceleration vector. And for most paths, t is r prime over magnitude of r. So you got this denominator with a square root and a bunch of squares in it. So calculating t prime gets a little bit hairy because of that denominator. Then calculating the magnitude of t prime further complicates the thing, and we get a very complex expression for the unit normal vector. And there are easier ways, and then it simplifies usually. So, but there are easier ways to calculate it. It's good for everybody's soul to calculate one like this, or two or three. I filled a lot of pages calculating these things till I was sure I had the idea. In any case, there's your unit normal vector. These two are perpendicular, so you've got a right angle between this vector and this vector. If you then do a cross product, you're going to have a vector at right angle to both of them. And I'm drawing it too long. That vector will be a unit vector. And that's called the binormal vector. Unit tangent vector cross unit normal vector. Binormal. So you can imagine you've got your unit tangent vector, your normal vector and your binormal. There they are. And you're going along this curve. Okay? Your unit tangent vector, if you're driving your hybrid airplane car and you're going through the air in 3 dimensions, okay? If you're looking forward, you're always looking in the direction of the unit tangent vector, assuming you don't get a little yaw or whatever that is in your motion. Hopefully, you're always looking in the direction. If you're driving your car on a road, you're pretty much always looking in the direction of your unit tangent vector if you're looking straight forward. Unit normal vector is perpendicular to that direction. It's to your left or right, depending if you're going around a curve to the right or left. If you're up in the air, you can also be going around a curve that looks like this, like on a roller coaster. It's another way to think of it. And you have this binormal vector, which is the direction that should be up the way you're sitting, but if you're in a twisting motion, it isn't, okay? And the relationship between this vector and upward is a lot related to your orientation. And that's something you want to think about next time you're flying around. Okay, so this is kind of a coordinate system. The unit tangent, unit normal, unit tangent, unit normal, and binormal form a coordinate system, and your acceleration vector is somewhere within that system. Now, just to take this a little too far, so if we've got our unit tangent vector, our unit normal vector, and these angles aren't exactly right angles because we're drawing in 3 dimensions and we don't even know what the orientation is. But imagine unit tangent, unit normal, binormal. Okay. And we have our acceleration vector. So let's just say our acceleration vector is like so. At this point. That acceleration vector projects onto the direction of the unit normal and the unit tangent. So whatever the direction your projection lines are, you might have this and you might have this. You now have components of the acceleration vector which could be denoted A normal, and over here A parallel. The components of your acceleration vector, and your acceleration vector, of course, then is and the magnitude of these components is just A dotted with N. That's going to be the projection of your A vector on N because of the definition of dot product. If this is your angle between A and N, then this is the magnitude of this times the cosine of this angle. This is the adjacent side to this hypotenuse. And this is the opposite side to this hypotenuse if this is the angle. Or, I forget what I said about opposite, but just same thing for the tangent vector. For the parallel vector, A parallel is A dot T. Now, what I've got here is the magnitude of A parallel and A normal. The actual normal vector is easily calculated. the magnitude of A dot n multiplied by the unit vector in the direction, which is just n. So this normal vector, or this normal component, has a vector. The normal vector, the vector that represents the normal component, has magnitude equal to its magnitude, but it has a direction of n, so you multiply its magnitude by n, and same with tangent vector. So these are very easy to calculate once you have all your vectors. And then there's another vector, or another function that's important. It's the rate of change of your B vector. If I'm driving along a straight road, or even if I'm driving in a plane, my B vector doesn't change. If I get on the side of a hill, tilt this way, and my B vector changes. So it tells you at which, the rate at which your orientation with vertical, in that case, or whatever, is changing. Okay. So this is all important for understanding motion in 3 dimensions, and well worth, I think, viewing this video before you get into the assignment.